So, like, if I have let's imagine I just have a 1D bar and I'm going to solve the elasticity equation, or I'm going to solve the elasticity equation of the bar we looked at last time, like EA times partial squared U, that thing, right? So if I have this, if I had some function of E, right, that was highly heterogeneous, right, then my solution is also going to be, so then U of X would also be kind of weird, right? And so as long as my solution is smooth, if I keep going up in polynomial order, maybe eventually I can get something that kind of matches this thing, right? The problem with polynomials is that they do oscillate some. So even if I had, say, a discontinuous E, right? So if I had a discontinuous E, I could still use some approximating polynomials, and if I went high in order enough, perhaps I would get a solution that could match this pretty well, but there's always going to be like some oscillation, right? Just due to the nature of polynomials. So in one dimension, you could imagine that if I just keep going higher and higher order, except for some small oscillations that would cause errors in the solution, that maybe I can match things. But when you go to 2D, it's very difficult. So imagine I have a two-dimensional domain that looks like that, right? Well, now it's pretty difficult to conceive of some interpolating polynomials that are going to be able to, like, match the boundary conditions and get like a good field solution over this domain. But what I can do is I can break it up, right? And if I break it up, then I have kind of two simple geometries that I can define well-defined polynomials on, and then use superposition to add them together, right? So, and so now, we're going to introduce the concept of elements, right? And we'll work on, finite elements from now on. Okay, so what we're going to do first, we're going to try to come up with a systematic way of developing these basis functions, which from now on you'll probably hear me call shape functions. That's the common terminology in finite elements. So, and it makes sense why. Like it's the shape of the assumed solution over the element, right? It's a linear, it's a quadratic, something like that. And so we'll start with a domain. And we're going to break that domain up into two elements of equal size. Maybe I didn't draw that quite equal. So this is the global domain. Then this is the domain of element 1. This is the domain of element 2. And I'm going to number my nodes. So these are now nodes that separate the element, right? So this is going to be the elements. So this will be 0, this will be 1, and this will be 2. And then I'm also going to number my elements. So my elements will be 1 and 2. Okay, and I'll use the circles around the numbers to indicate the element number versus the node number. So the length of element 1 is going to be XA, and the length or position vector to the second node will be XB. And so then what we're going to do is we're going to pull out element 2. So let's look at element 2 over here. So this is the domain of element 2. The nodes are 1 and 2, and this is element 2. So if we write down that we want u of h to be equal to c1 plus c2x, then let's evaluate u of h at the nodes, at the nodal locations. Okay? So I'll just write that out. We're going to evaluate the field at the nodes. When I say the field, I mean u, right? U. And I say field there because, you know, it depends on the problem domain, right? U in this case is just sort of a generic field variable. But if I change the physics of the problem, it could be temperature, it could be pressure, right? So we'll just say we're going to evaluate the field. Node 1, we have u at xa is equal to c1 plus c2 at xa. And we're going to define this to be u1 e2. At node 2, we're going to evaluate u at xb, c1 plus c2 xb, and this will be u2 e2. So if we write those equations in matrix form, we have u1 e1, or e2 rather, u2 e2 is equal to 1 1 xa xb times c1 c2, or in matrix form this would be u of e2 is equal to what we'll call a times c, right? And that thing has the solution, c is equal to a inverse times u. So for this problem, if we worked it out what C1 or if I wrote down what C is for this, and we could do it symbolically in Mathematica or whatever, but I'll just write down the solution. We'd have a vector u2 e2 xa minus u1 so that's C1, and here so that's a vector. This is C1, this is C2. And we could use those, we could plug those in to our function then. And here then the unknown coefficients would be, or the, well, let me not say that. Okay, so I guess, yeah, let's just write it out one time. That plus Okay, so we have that thing. All right. Now, from now on, so I'm going to write that u of h is equal to, and I think I'd written this in one of the earlier slides when we had the approximation. Now we're going to say that this is equal to uj, the sum, u of h is equal to the sum over the elements, well, the nodes rather, the j nodes, the nj, uj. So if you remember, in the original description I had something like this, you know, phi c, right? But now we have nodes, right? I said we can't, these uj's are associated with the nodes, right? Well, the u's up here, these are the nodal displacements, right? Okay, so now I'm going to write this thing. Now we'll ignore the second term because now we've discretized the problem. We have nodes. I'm going to say that it looks like that. And of course, then you could write this as N1 U1 E2 plus N2 U2 E2 or taking this equation and writing it in this form, basically pulling out the U's, 1's, and U2's, I'm going to have so this is N1, and this is N2. So let's just, for now, let's let xb minus xa equal to L. So it's like the length of the element. So then we have u of h is equal to 1 minus xl plus times u1 e2 plus x over L u2 e2, or everyone would be okay if I wrote this as 1 as a vector, 1 minus x over L, comma, x L, a row vector times u1, e2, u2, e2, right? Then this guy is in vector, right, transpose. So this is like shape function vector. Yeah, we got time. All right. So let's just real quick look at a quadratic element. So here, in a quadratic element, we're going to have 3 nodes. 2 of them are at the boundaries, and then there's one interior element, a node, one interior node. So this is 1, 2, 3. Again, this distance is x, and we'll assume that the overall distance of the element is L, so this is L over 2 and L over 2. So let's write down u of h is equal to nj uj And that's equal to, we're using quadratic interpolant now, so C1 plus C2x plus C3x squared. And if I let x transpose be equal to 1x x squared, then I could also write this as x transpose times c, right? So if I let one x squared, right? So the polynomial basis, and then then this equation becomes x times c, where c is the c1, c2, c3, right? So I'm just writing this in matrix form. Okay, if we did that, what we would get is u1, u2, u3 equal to 1, 0, 0, 1 L over 2, L over 2 squared, 1 L squared times C1, C2, C3. And then in matrix form, this will be U is equal to A times C. Right? We wrote that again up here, right? So it's just doing that now for the quadratic case. Okay, so from the vector form of this and the vector form of this, let's write that down. So we say that N transpose U, so this is just the vector, this is a vector statement of Nj Uj, right? So, and we know that Nj Uj is equal to that thing, which is equal to X transpose C, right? So if we substitute in for U, AC, so we have N transpose AC equals to X transpose C, well, these are vectors, right? Well, the C's will cancel, and then I can multiply on the right-hand side by A inverse, right? So inverse equals X transpose A inverse. These become the identity matrix, and so then ultimately I have N transpose is equal to X transpose A inverse. And so another way you can think of this is X transpose, right? X is just your basis, right? 1x, x squared. It's like a vector of the basis, right? Then what A is X transpose evaluated at the nodes. X equals x1, evaluated at x equals x2, and evaluated at x equals x3. And so this gives us a systematic way to develop the shape functions for any order polynomial basis, right? So if you look at this is this, right? And what is this? Well, again, my basis is 1x x squared. I evaluated it at the first node. The location of the first node is 0, right? So that gives me 1, 0, 0, okay? Location of the second node is L over 2, so then I have 1 L over 2, L over 2 squared. And third node is at L, so I have 1 L squared, right? So that A matrix is just my basis evaluated at the nodes, okay? So let's see what it looks like for this polynomial set of basis functions. So what we'll do is we'll define x to be 1x x squared, okay? And then a is going to be equal to x evaluated at the first node, which is x equals to 0, and then x evaluated at the second node, which is x equal to L over 2, and then the third will be x evaluated at x equal to L. Okay? And it's a matrix. So we'll look at it in a matrix form, right? So everybody agree, that's what I wrote down. Okay. So then what did I say? N is equal to x times the inverse of A. That's my base. Those are my quadratic basis functions. You want to go cubic? All you got to do add a cubic term there. So now our element would be divided. Now you'd have two interior nodes. So you'd have L over 3, 2L over 3, and then a new term, x at L. There should be 4 terms. Oh, I didn't read about, wait, that guy. There we go. Just like in a Jupyter notebook, if you go back, you got to evaluate all the cells, right? So now we got that, and then that's my quartic basis. Right? And then again, these are the basis functions. Everybody see there's 4 of them now. 1, 2, 3, 4. And so then I can use that here. Right? So I have a systematic way to develop the basis functions. Right? And the same way when we get to 2, we're going to first solve some 1D problems. When we get to 2D, it's basically the same idea. Except instead of having in vector, you have an in matrix. It'll involve terms of x and y. And same thing if you went to 3D. So, yeah. Sounds simple? I mean, there'll be a homework problem, but I mean, I think it's pretty simple, right? Especially, I mean, if you look at the code, that's what's important, right? Yeah. Right? Basically, you just define your basis as a vector. Now, in Mathematica, the default, like, I don't have to transpose it because, like, in class when I write a vector, I'm always assuming it's a column vector, so then I said x transpose. In Mathematica, if I want a column vector, I'd have to put an extra set of squiggly braces around it, and then I would have a column vector, and then I would have to transpose it. But in this case, it's already a row vector, so I don't transpose it. So I have a row vector, I just define the basis, 1x, x squared, x cubed, and then just evaluate the basis at the nodes, right? Evaluate x at x equal to 0, at x equal L over 3, at 2L over 3, and at L. That gives me A, and then just x inverse A, and you get the basis. You got your basis functions. Now you have U of H, right? U of H is in this thing times the unknown nodal values, U1, U2, U3, U4, plug that into my bilinear form. We'll talk about that next time, but plug that into my bilinear form, and then ultimately, and this is the last thing I'll say, once we do that, well, convenient that it's there, because I wrote it in the wrong. Ultimately, once you plug everything in, evaluate the integrals, remember the unknown u's are constants, so they'll move out of the function, and what this B matrix will be a matrix K times a set of unknown nodal values, U, equal to, whatever you want to call this right-hand side, F. And then we can solve the equation. It's just